All right, another video about Z3. I okay. I need to make an assignment for university, and one of the exercises is, I think you could describe it as a rectangle packing problem. Uh, so this is just a basic version of the final thing, but it works as follows. You get a grid size and a number of rectangles, and then you need to figure out there is a way to lay the rectangles on the grid. Basically, it's a super intuitive problem, but it took me a really long time to figure out. I think I worked on this for like a little over 10 hours. I don't really remember. So yeah, I'll show you how it works. Okay. Yeah. I set it up so that it runs through a bunch of permutations. So there's some stuff that's said that's not entirely relevant. So I'll first go through my solution. I thought I would record it right after I've made something that works, because otherwise I'm gonna forget how all of this works, right? So the solution is actually fairly short. So I created a separate solve function that you can plug the data into. I mean the exercise assign data, basically, like so sizes is an array of pairs of sizes, well, where the left argument, I mean where the pair is the width and the height. Very simple. And then size is the size of the grid. Then all of these are helper functions. I don't think I'm going to explain all of it. I think one thing that took me the longest for this problem is actually figuring out how to display the results, because I kept drawing them on a piece of paper, and then it just takes an enormous amount of time to figure out how the program is messing up, because the output of Z3 is just a bunch of variables, and it's quite hard to read. So turning that back into like a little picture, like this thing, was hard. But I guess that's not much to do with Z3. I mean, a little bit, because I had to like parse the output and stuff. But I don't think I'm going to cover how all of that works. So this is basically the solution. So it's very, very succinct. It's only, I don't know, 50, it's only 14 lines apparently or something. I mean, of actual content, I guess. I mean, about 20 lines, let's see. So first, I call this Z, because at first, I don't really remember. Oh, yeah, okay, because these are all, they all live in the plane, essentially. But I just used Boolean variables this time. So you basically have a cube of variables, sort of. Yeah, I think that's a cool way to think about it, right? So you have a X and Y grid, and then you have layers for every rectangle, which is here the R value. And then every box in your 3D grid encodes that the lower left. Okay, maybe I have to draw this out because this is more complicated than I thought. The lower left corner of your rectangle falls. Yeah, if let's say Z000 is true, that means that the the first rectangle in your assignment area, like in your sizes area, I called it, So, okay, let's grab the data here. So if in that big grid of variables, right? If z 0, 0, 0 is true, what that means is, in this case, the rectangle 0 has size 1, 2, and its lower left-hand corner is placed in box 0, 0 on your grid. But then it took me a long time to figure all of this out. Yeah, then you don't want to duplicate rectangle 0 twice. And you also don't want not to use it, because then the problem, you would rather have it spit out that it's unsatisfiable. It also took me a while to figure out. At first I wrote here less than, but then it kept just giving me solutions without all the rectangles. That took me, so it's kind of embarrassing how long it took me to figure out that mistake. But yeah, figure it out. So basically what this says is loop over all the rows in the grid, and then for each row, loop over the columns, and do that for every rectangle. Yeah, and for every rectangle, the whole grid has to equal 1, basically, because you can only place it once, and you don't want to place it 0 times, because then you've not solved the problem. So I think, yeah, once you've solved it, it looks very simple. But man. And then this one also took me. Yeah, this one was. I think this was by far the hardest part of trying to figure this out. So I wrote a. Okay. I'll explain what it does. So here I loop over the grid. So basically, in this scope here, I have XP, YP is the current cell we're looking at. And then for every cell, you loop over the rectangles. And over all possible placements of the rectangles. And if one of the rectangles, and none of the rectangles are allowed to, every rectangle is only allowed to intersect that square at most once. Because if two rectangles both cover that square at the same time, then you have two booleans there, which means, then you have two rectangles that overlap. So this covers function, it's a predicate that takes an R, and then inside of the function that is used to take out the width and the height, the width and the height, yeah. And then it checks if the rectangle R is placed at XY, does it cover the point XPYP? Okay. Yeah. So maybe I'll go over it again very fast. Already kind of fast. Maybe I should record the time while I'm doing this, because I have no clue how long this is going to be. So you loop over all the squares. Then for every square, you loop over the rectangle, over all rectangles. And then for every rectangle, you loop over all squares that are covered by the current rectangle at the current point. And if the sum of those is less than or equal to 1, that means no two squares overlap at the point XPYP. That's all. Then I think that was, yeah, so that was basically how I solved it. Yeah, all the rest is also, it took me more work to actually get to grips with like what it was doing and why it was messing up, as opposed to actually solving the problem. Because actually solving the problem took a lot of ingenuity, but I found a resource that explained it quite well. But then I mean, it not applied to Z3, just for SAT solvers in general, which is also, there might be a way to do this more elegantly using integer variables, like encode every square just as a pair of integers. But yeah, I think the solution is pretty interesting and it works really well. It runs fast. I mean, I've only tried it with small amounts of data. But yeah, as you can see, for example, I'll show you what it does to prove that it actually works. Here I say the grid size is 3, so it draws a 3 by 3 grid. And then you get a list of rectangles. And I set it up in such a way that it exactly covers the grid. So you have, basically you have 4 domino tiles and 1 square tile. Oh wait, yeah, 1 square tile. And what's also funny is D3 always places the square tile in the middle, and I don't know why. Yeah, I also learned some other things. I figured out if you pass it the same input data twice, it always does the exact same thing, which I find curious. I don't know why it works that way. It's useful in some cases, but for me, let's say I wanted to find like random tilings or random ways to place down these tiles on a grid. I don't know how to go about that because you can't just run the program twice because it's going to come up with the same answer. That's why I wrote it like this. I loop over all the permutations of the tiles of the rectangles so that I can, when the program wasn't working yet, I could see the different ways in which it was making mistakes, which really helped. But yeah, that's it. I hope if I rewatch this, I understand what I made. And see you later.